2 coupons. Each unit of good Y costs 1 coupon. So those are the coupon prices. Now, maximize utility subject to these 2 constraints. Let me write it out. Subject to, what would the 2 constraints be? How would you write the income constraint? Okay, now we'll just modify that a little bit for this problem. For the moment. Yes, yes. For the moment, let's assume that. Later on, we'll make that assumption that you made that they're actually equal. What's the other constraint? That is just the income constraint. What's the other constraint? How would we write that?
2x plus y.
Yes. 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 Okay. And then we would also have these conditions, of course. The non-negativity conditions. The amount of X and Y you consume can't be negative. Okay. All right. So what is our Lagrange function now?
This 200 you wrote over here, is this supposed to be 120? Or
Oh, did I write 200? Thank you very much. This is supposed to be 120. Sorry. I made a mistake there. Thank you for correcting that. Because the coupons are 120, not 200. I was thinking of maybe the homework problem. I think in the homework problem there were 200. No. Let's do this one. Okay, so what's our Lagrange function now?
xy
xy.
minus 1 times 100 minus x minus y.
Yes.
Plus lambda 2, 120 minus 2x minus y.
Exactly right. Right. Okay. All right. So what's our Kuhn-Tucker conditions? Look at partial z, partial x. What would partial z, partial x be here?
Y minus x minus 2x.
Y minus, what did you say?
Lambda 1x.
Yes, minus lambda 1. When you differentiate, it would just be lambda 1, wouldn't it? Yeah. Okay, I know it's getting late. It's Friday. Okay, what's the rest of it?
Minus 2 lambda 2.
Minus 2 lambda 2. Now, let's follow your suggestion, Kelsey, and let's assume that this constraint is, this income constraint is exactly binding. That would be an obvious assumption to make, because if x were 0, utility would be 0. So you're going to spend all your money. Okay. So let's assume this is 0. Okay. Partial z, partial y. Or I shouldn't have said that. I shouldn't say you're going to spend all your money. Forgive me, that was wrong. But the value of x is going to be positive. So that means partial z, partial x is going to be 0. Okay. By complementary slackness, x times partial z, partial x must be 0. So okay. So partial z, partial y is going to be what? X minus lambda 1 minus, what'd you say, Zachary?
Lambda 2.
Right. And let's assume that is 0. In other words, let's assume the value of y is not 0. That's all we're assuming. Here, this means the value of x is not 0. This means the value of y is not 0. We don't have a corner solution. Partial z partial lambda 1 is what?
100 minus x plus 1.
Yes. Now, if we assume that, so we're going to have to make some guesses here. So far, the only guesses we've made are that x is greater than 0, y is greater than 0. If we want to assume that you're going to spend all your money, then what would that mean about this equation right here?
We could set it equal to 0.
Yeah. So let's just try that. Let's try that. So let's assume lambda 1 is positive. Okay. That would imply this. But this is a guess, and we may have to go back and change this. Then partial z partial lambda 2 is what?
120 minus 200 plus 5.
All right. And let's assume that you're going to use all your coupons. So let's assume lambda 2 is greater than 0. So then everything's just an equality. So let's see what we get. Okay. From these two equations, notice you could solve for x and y. And what will we get? Let's just use Cramer's rule. And we could rewrite this as x plus y equals 100. We could write this as 2x plus y equals 120. So if we use Cramer's rule, we could get for x star equals, let's see, this determinant down here would be 1, 1, 2, 1. Up here, we would have this determinant 100, 120, 1, 1. So this would be 100 minus 120 would be minus 20 up here. This is 1 minus 2 would be minus 1. So it's 20. Okay, that's good. It's positive. So let's see if we could get a positive value for y star. Y star would be this. Same determinant down here. Up here, we would have 1, 2, and then we would substitute in these constants, 100 and 120. Let's see what we get here. We get 120 minus 200, what, 80, minus 80? Okay, and down here we have minus 1 equals 80. Okay, good. We got positive values for x, positive values for y. That's consistent with these two assumptions, that these are equal to 0. Now we got to worry about the lambda 1 and lambda 2, though. Got to make sure they're positive. Okay, so let's rewrite these equations right here. We're assuming these two equations hold exactly. So we could rewrite this as lambda 1 plus 2 lambda 2 equals y. Right, and the second one is lambda 1 plus lambda 2 equals x. And let's see, what did we get for y just a minute ago? We got this y star was 80. X star we found was 20. Okay, all right, so let's go back to this. Let's use Cramer's rule here. So we're solving for lambda 1 star. And here we have this determinant 1, 1, 2, 1. Up here we have We have this one first, 80, 20. We have a 2, 1 here. So what do we get? 80 minus 40 is 40. Here we get 1 minus 2. Minus 1 minus 40. That means we made a mistake somewhere. One of our assumptions was wrong. Let's look at this. This will help us figure out what the wrong one was. Lambda 1 is minus 40. What is the interpretation of lambda 1 here? Right, so it's negative. So that means the marginal utility of income is actually negative. So let's assume that lambda 1 is not, let's assume lambda 1 is 0. Let's go back and assume lambda 1 equals 0. Because we got a negative lambda 1, that's a problem. So let's assume it's 0. Okay. So now we go back to these two equations and see what happens. From this equation here, notice what we get. Y minus 2 lambda 2 equals 0. Y star was equal to 80. So this would be 80 equals 2 lambda 2. Lambda 2 star is 40. That's good. But now we have to worry about this. Lambda 1 is 0. So this drops out here. So x star, or lambda 2 star, that's it. That's it. Lambda 2 star was positive. We don't have to. Lambda 1 star we already assumed was 0. So this works. Lambda 1 star is 0. That's okay. Lambda 2 star is 40. The only thing we have to go back is our x and y values. Let's assume, let's look at partial z, partial lambda 1. This actually should be greater than or equal to 0. Okay. Partial z, partial lambda 1, excuse me. This is equal here. This should be greater than or equal to 0. Okay, let's make sure this holds. If we have, this is 100, x star was, what was x star? Oh, yeah, we got it, 20. Wait a second. Uh-oh. No, we made it, I'm sorry. That would be 0. Okay. Okay, wait a second. Okay. Oh, our y star, what was our y star value? This was, okay, wait a second. I'm sorry. I went through this too quickly. If we assume lambda 1 is 0, then this y star is equal to 2 lambda 2. Okay. Here, x star is equal to a lambda 2 star. So what does that mean about y and x? That means y star is 2x star. Okay. And actually, isn't that what we found before? Oh, okay.
Yeah, y star was equal to 80 and x was equal to 20 and stuff.
Okay. Wait. When we solve for x and y from these equations, okay, though that's the trouble. These equations don't hold exactly. Okay. This y star is 2x. Okay, so let's go back to this equation. This one holds exactly. Here we go. So 120 minus 2x star minus y star. Y star is 2x star. Here we go. 120 equals 4x. So x star equals 30. There we go. That's what we had to do. X star equals 30. Y star is therefore 60. So let's go back and get our lambda star values. We used the wrong ones before, didn't we? Let's x star, y star, we've now found is 60. 60 minus 2 lambda 2 equals 0. So lambda 2 equals 30. Okay, not 40. I was using the y star value we got before. Should be 30. Okay. Lambda 2 star is equal to 30. So that means y star right here is equal to 60. Okay. All right. So x star is 30. Now that works, doesn't it? Because then this constraint is exactly binding. But this constraint, if x is 30 and y is 60, this constraint is equal to 10, which is greater than 0. So that's okay. So in this case, you don't use all your income. You don't use all your income. You only use $90 worth of your income. Okay, your income is 100, but you only spend $90. Your coupon constraint is exactly binding. So in a picture, let's see what this looks like in a picture. Here's x and y. Our budget constraint is from 100 to 100. That's our income constraint. Label that with an I. What does our coupon constraint look like? Our coupon constraint looks like this. Our coupon constraint is y equals 120 minus 2x. So it looks like this. This goes like this, would cross at 60 down here. These two intersect right here. Where are you at? You're at the point where y is 60 and x equals 30. So you're at this point right here. You're right here. So you are inside your income constraint. This line is your income constraint. You are inside it. Means you're not spending all your income. Okay. That's consistent with our solution that lambda 1 star equals 0. Okay. See our feasible region? You have to satisfy both constraints. Here's the income constraint. Here's the coupon constraint. It's the coupon constraint that's more binding in this case. The income constraint isn't binding. So you actually maximize your utility by consuming along this segment here, which means you're not using all your income. Okay. If you were actually to be at this kink point where you're exactly satisfying both constraints, you would be at a lower level of utility at this point right here. Okay. Does that make sense? Okay. So it's somewhat of a guessing game. You make assumptions first about x and y, in the examples I've done, we assume that they're both positive. So that right away tells you that partial z partial x is 0. You assume y is positive, so that led us to this. Okay. Then we assumed that lambda 1 was 0. So that led us to this conclusion, that partial z partial lambda 1 is just greater than or equal to 0. Or, yeah. Or actually, partial z partial lambda 1 is actually positive in this case. Okay. Well, actually, it could be exactly 0, so I'll just put that. We assumed that lambda 2 was positive, so that means partial z partial lambda 2 must be exactly 0. Okay. All right, those were the correct guesses. When we initially assumed that lambda 1 was positive, then we ran into problems. If you assume lambda 1 and lambda 2 are both positive, that means you're at the kink point. And at this kink point, we solve for our value of lambda 1, and it actually turned out to be negative. So that was inconsistent with the Kuhn-Tucker conditions that lambda 1 be positive or possibly 0. Okay. All right. Okay. Do you think you have enough now to go ahead and finish that homework problem in 641? Okay. You could actually just do this graphically because you know what your feasible region looks like. Your feasible region looks like this. Here's the intuitive way to do it. Here's your budget constraint. Here's your coupon constraint. So your feasible region where you satisfy both constraints is this kinked area right here. So at first the slope is -1, then it changes to -2 right here. And then just see what is the highest indifference curve you can reach. And it so happens the highest indifference curve you can reach is this one right here, which is tangent along this segment right here. Okay. For this problem. Of course, your homework problem might be slightly different. Okay. That's all for today. I hope to see you all later tonight at Jeremy Bray's barbecue.
Is it tonight or the 11th? Next week.
Oh, is it next week? Oh, I'm sorry. I'm glad you told me.
Freaks me out.